Hi viewers, welcome to all. Here we are discussing about a project, the probability driven evaluations of lower part approximation adders. Here, the carry chains may sometimes represent a critical paths in parallel prefix adder topology, which can restrict speed and results efficiency. We examined several approximation strategies that reduce the length of the carry chain by offloading the lower part of the computations to the more approximation unit. Using probability theory, we are able to develop more number of models of the correctness. In addition, the work will present and the article provide a novelty based majority gate using half adders as well as the majority gate using full adders as well as the majority gate of half adder using XS1 converter. Okay, so these three designs we have included in the lower part approximation adders. Okay, that is a proposed novelty of this work. Okay, in addition to create a LXOA approximate adder employing novelty based majority gate full adder, half adder and XS1 converter with the goal of reducing the number of errors in additions output to the current LOA and LXOA approximation adder. Okay, so in the final, this work was proposed using Verla HDLs and each parameters was evaluated based on the impact on the area, latency and power consumptions. Okay, now we can verify the base paper. This is a base paper title and the abstract document. Okay, so probability driven evaluations of lower part approximation adders. Okay, this is a concept of this work. So here what they are doing means they are taken two approximation adders. Actually one is the existing and another one is a proposed. Okay, so here this is the existing adder, that is a LOA. Okay, so lower part or gating adder. Okay, so and section B is a LXOA. Okay, so lower part XR and OR gating adder. Okay, so these two adders they are given. Okay, so here they are splitted that adder in two configurations. One is the accurate part, another one is the inaccurate part. Okay, this inaccurate part will provide the carry input to the accurate part. That is the concept, but this will take a more carry length and carry problem will create a error mismatches in the accurate part. Okay, so here they are concentrate on the carry part only. Okay, so here the LXOA adder you can check they are additionally added with the half adder. Okay, so this is a half adder for LXOA. Okay, so here this half adder they are taken separately and they are given an input a k minus 1 and b k minus 1. Okay, and they are taken as a scene. Okay, so we are proposed this architecture. Okay, and we are design a new novelty based one. Okay, here this accurate adder means it's a chain of full adders. Okay, then only we can get a accurate output. Okay, so here accurate adder means we can use full adders, but here we are modified the full adder using a majority logic gate. Okay, so that majority logic gate full adders we are used on the accurate adder. Okay, and additionally the half adder also we are designed with a majority logic gate. Okay, and we are checked the final output. It will take most of cases 1 bit error will be occur in the LXOA output. Okay, that's why we are used a XS1 converter in the output. Okay, to reduce that 1 bit error. Okay, so we are proposed the architecture and it will be present on the Verla HDL coding. Okay, now we can verify the coding part. Okay, so this is the first one, LOA 8-bit conventional full adder. Okay, so this is a test bench of the coding, the top model accurate part and inaccurate part. So here this simulation part we can check it. Here this is a clock and reset A B. You can check the output. The first one 7525. Okay, you can add it. Okay, the normal value of data check value is 100. Okay, 75 plus 25, but this sum value of LOA it will provide a 107, 109, 111. Okay, you can check all the values. Okay, 77 plus 29. Okay, and you can check the error distance. Okay, 7311111. Okay, so this is the LOA architecture. Okay, and the second stage is LXOA. This is a LXOA architecture. So here they are used additionally with a half adder. Okay, that half adder based simulation, it will be present on here. So here you can check the input and output. This is a and this is a B, sum value and data check value. Okay, so here you can 75 plus 25, we can get 100, but here the output will be present on 99 and 101111. Okay, so you can check the error distance 151111 continuous one, right? So we can reduce this errors in the proposed architecture. The proposed architecture code is, we are used a test bench, and this simulation we can show it on here. Okay, so here you can check the clock, reset, A, B, okay, sum value, data check value. Okay, it will be same 100. Okay, and you can check other values. Okay, so we are reduce the number of error distance. Okay, here first one is error is 0, second one is 4, and continuously 0, and here only it will be present on 4. Okay, and continuous 0. Okay, so we are reduced the number of errors in the proposed one. Okay, and this synthesized report, we are synthesized in vertex 5 FPGA. You can check it. Okay, so here this one is a LOA 8-bit conventional full adders. Okay, so here LUT will take 13, occupied slice will take 16, and IOB will take 24 bit. Okay, and delay will take 7.346 nanosecond, and this is the RTL schematic for LOA, accurate part and inaccurate part. Okay, and next one is a LXOA. So here you can check it, number of slice registers 15, occupied slices 14, IOB is equal to 24, and synthesis report you can check delay equal to 7.346 nanosecond. Okay, you can check the RTL schematic. This is the RTL schematic. It will be present with the accurate part, half adder and inaccurate part. Okay, and the next one is a proposed one, design with a majority gate. Okay, so you can check the number of slice LUTs, okay, number of occupied slices, okay, number of IOB. Okay, and you can check the RTL schematic. Okay, so this is a RTL schematic, and you can check the proposed one. Okay, accurate part, half adder, majority gate, inaccurate part, and XS1 converter. Okay, so this accurate part, it will be present with the full adder majority gate. Okay, you can check the full adder majority gate architecture on here. Okay, so 3 majority gate will be present on the full adder architecture, and the half adder majority gate, you can check it on here. This is a XS1 converter, and half adder majority gate you can check it on here. This is a half adder majority gate, and this is a full adder majority gate. Okay, and this comparisons we are updated here. Here you can check additionally with the 8-bit triple carry adder design and 8-bit LOA approximate, 8-bit LXOA approximate adder design, and 8-bit LXOA with the majority gate approximate adder design. Okay, so you can check the number of comparisons and LUTs, occupied slices, and delay and power. Okay, and this is a comparison analysis chart. Okay, we have written an abstract document for this project. So here this is a abstract document, base paper abstract, enhancement of this project, and proposed title and proposed abstract, existing system, disadvantages, proposed systems. Okay, and this is the architectures we are given, the majority gate, full adders and half adders. Okay, and related notes for this project, and literature survey, finally references. Okay, thank you.
If you need more video related with VLSI projects implementation, please like and subscribe this channel.